Let's move on to section 1.3, radicals and rational exponents. So when we have square roots, when the square root of a number is squared, the result is the original number. So since 4 squared equals 16, we can say that the square root of 16 is 4. So in general terms, if a is a positive real number, then the square root of a is a number that when multiplied by itself gives a. You can square a positive number and a negative number and it will give you this same outcome, but for this class we're going to use the principal square root, and that is the non-negative number that's multiplied by itself that equals a. And the square root that's obtained when you use your calculator is the principal square root. The principal square root of a is written as the square root of a. The symbol is called a radical, so this is the radical. The term under the symbol is the radicand, and then the whole thing is the radical expression. And the difference between an expression and an equation is that an equation has an equal sign. So here's our formal definition. The principal square root of a is the non-negative number that when multiplied by itself equals a. It is written as a radical expression with the symbol called a radical over the term called the radicand, and that gives you that. So there's a question here: does the square root of 25 equal plus or minus 5? And the answer is no. I would say not yet. So although both 5 squared and negative 5 squared equal 25, the radical symbol implies that only a non-negative root, the principal square root of 25 is square root of 25, or 5. So let's evaluate each expression. So the square root of 100 equals 10 because 10 squared equals 100. Now, if it is a perfect square, like 100, it's going to show up on your calculator. So you're going to hit, so I have a TI, so anything is color-coded, so my square root symbol is in orange or yellow, orangish yellow, so I have to hit the second button for it to happen. So second square root 100 in my parentheses, and it gives me 10 as my answer. But that is not always going to be the case in this class, because you're going to have things that don't always make nice pretty square roots. So this is the square root of 16. So we're going to start inside first, and that gives me the square root of 4, and that's because 4 squared equals 16, and then that becomes 2 because 2 squared equals 4. So here I'm going to go ahead and add these first, and that gives me the square root of 169, and that gives me 13 because 13 squared equals 169. So here I'm going to figure this, and then go ahead and subtract them. So the square root of 49 is 7, the square root of 81 is 9, and that gives me -2. So here's a question: if for this problem here, can we find the square roots before adding? And the answer is no. So if I take the square root of 25 and add the square root of 144, I get 5 equals 12, which is 17. And that's not the same as adding them first to get the square root of 169, which is 13. In the order of operations, we have to add the terms in the radicand before finding the square root. Alright, so here's a product rule for simplifying square roots. So the square root of a times b is also the same as the square root of a times the square root of b. And in math, if a rule goes one way, it goes the other way. So I can also have two things multiplied and put them under the same radical. So this says how to, given a square root radical expression, use the product rule to simplify it. You're going to factor any perfect squares from the radicand, write the radical expression as a product of radical expressions, and then simplify. So the square root of 300 is the square root of 100 times 3. So that's the square root of 100 times the square root of 3. And this is a perfect square. And so that's 10 times the square root of 3. I'm pretty certain if you did a Google search list of perfect squares, it would give you the most common ones if you don't know them already. The more you work with them, the more you're going to recognize them. So this equals the square root. So this is 2 times 81. And this is a to the 4th times a, and then b to the 4th. So this is the square root of 2 times the square root of 81 times the square root of a to the 4th times the square root of a times the square root of b to the 4th. So we can't do this, stays the way it is, but this becomes 9. This becomes a squared. This stays the way it is, and this becomes b squared. So this becomes the 9a squared b squared times radical 2 times radical b to the 4th. And we're going to go ahead and put those under the same radicand. So 9a squared b squared times the radical 2b to the 4th. Oh, look what I did. I wrote that down here instead of b squared. Shame on me. Let's start this one over. So this, I don't know if this happens to you, but I've been working a long time, and I'm trying to get something done, and I get tired and I make sloppy mistakes, and that's exactly what I'm doing in front of you on the camera right now. But that's okay. The good thing is I caught it, so let's go back through here. And I don't care how much math anyone knows, I don't care how much education you have, we all make silly errors occasionally. So let's look at this again. So we broke this down to 2 times 81, a to the 4th times a, b to the 4th. Why do I do a to the 4th times a? Well, that's because I want something even, so it's a perfect square. So this is root 2 times root 81 times root a to the 4th times square root of a times square root of b to the 4th. And that gives me square root of 2 times, so 81 becomes 9, a squared times the square root of a, and that becomes b squared. So now this becomes, these go out in front, 9a squared b squared times the square root 2, let's go ahead and put the extra step here, square root of a, and that gives me 9a squared b squared times the square root 2a. Alright, so given the product of multiple radical expressions, use the product rule to combine them into one radical expression. So we're going to express the product of multiple radical expressions as a single radical expression and then simplify. So I have this square root of 12 times the square root of 3, and I could do some stuff on that, but I could go ahead and multiply that as a square root of 12 times 3, and that gives me the square root of 36, and I know that 6 squared is 36, so that gives me an answer of 6. Alright, so here's a quotient rule. If I have a fraction underneath the square root, I can go ahead and break that up as the square root of the top divided by the square root of the bottom. So if I have an example here, this becomes the square root of 5 over the square root of 36. Can't really do anything with the square root of 5, but as we saw on that previous page, the square root of 36 is 6, and we leave our answer is that. Alright, that's kind of ugly. So let's go ahead and put that back under just one square root and see if we can simplify it. So 234 x to the 11th y over 26 x to the 7th y, and 26 goes into 234 9 times. So this gives the square root of 9x to the 11th minus 7, and y to the 1 minus 1. So that becomes the square root of 9x to the 4th, y to the 0, square root of 9x to the 4th, which gives me 3x squared. Alright, so when we add these, we can't add these unless they have the same number under the square root. At this point, we're treating them almost like variables, so you can't add x to y. So I need to see if I can simplify this first term a little bit more. So 5 square roots of 12 is 5 square root of 4 times 3, which is 5 square root of 4 times the square root of 3, and the square root of 4 becomes 2, which is 5 times 2 times the square root of 3, or 10 square roots of 3. So now I put that back into here, and I get 10 square roots of 3 plus 2 square roots of 3, and that gives me a total of 12 square roots of 3. Alright, let's look at another one. So I have square root of 5 here, but this is square root of 20. My spidey senses say that this is probably going to end up being some square root of 5. But let's go ahead and rewrite this. So I have 6 square roots of 20. That's a horrible square root. 6, I know 20 is 4 times 5. And 6 times square root of 4 times the square root of 5. 4 is a perfect square. So that's 6 times 2 times the square root of 5, which is 12 square roots of 5. I'm going to put that back into the equation. So I have the square root of 5 plus 12 square roots of 5. And so just like x is the same as 1x, the square root of 5 is the same as 1 square root of 5. So this gives me 13 square roots of 5. Oh, gross. Let's look at this one. Alright. It's not really gross. It's just going to be a little bit of work here. So, I'm probably going to have to work on both of them. This one looks a little less ugly, so I'm going to go ahead and see how I can simplify this guy. So I know 45 is 5 times 9, and 9 is a perfect square. So that's 4 times the square root of 9, the square root of 5 times the square root of x. So this would become 3. So this would be 4 times 3 times the square root of 5x, or 12 square roots of 5x. And so I bet 80, let's look at this term. I bet you, let's look at 80. If I divide 80 by 5, so I'm going to take 80 divided by 5, and that gives me 16. So that's 16 times 5, and 16 is a perfect root. So I have 3 times the square root of 16 times 5 times x, which is 3 times the square root of 16 times the square root. I'm just going to leave 5 and x together because I know they're going to not come out. And so this becomes 4, 3 times 4 square roots of 5x, or 12 square roots of 5x. And so I put this back in for my first term, this back in for my second term, and I get 12 square roots of 5x minus 12 square roots of 5x, and all that work for 0. Okay, so we have square roots used a lot. We can have other roots. So if I have a cubed equals 8, we want to know, we want to know what number raised to the third power equals 8. We know that 2 times 2 times 2 equals 8, so we say that 2 is the cubed root of 8. So you can also look up common cubed roots if you want in your calculator, or I'm sorry, on Google. So if a is a real number with at least one nth root, then the principal nth root of a, written as the nth root of a, is a number with the same sign as a that when raised to the nth power equals a. The index of the radical is n. Now if you notice that when we write a square root, we don't put a number there, but technically there's a 2. There's an understood 2. We just use it so often that we don't. Alright, so let's do negative 32, the fifth root of negative 32. So let's do a little factor tree. I know that this will be the fifth root of minus 1 times the fifth root of 32. And 32, if I do a little factor tree, it's 2 times 16. This is 2 times 8, 2 times 4, 2 times 2, and I know this is 1, 2, 3, 4, 5. So this becomes, that's negative 1, and the fifth root of 32 is 2, so my answer here is negative 2. Alright, let's do some more. So I'm going to go ahead and multiply this. They're both the fourth root, so this becomes the fourth root of 4096, and that one is a really big one. So how would I do that? I would actually probably put it in Symbolab. I would, or write a factor tree for this. And now that I'm thinking, the fourth root of 4 is, let's see, no, I can't do that. So let's make a factor tree for 4096, and let's think of, that's going to be a really long one. Let's look up, let's see, a number that will go into that. 4096. Let's put the right thing. Let's see if 8 goes in there. Okay, so that's 8 times 512, and that's 2 times 4, and that's 2 times 2. That's still really big. 512, let's see if 8 goes into that one. Yep, so that's 8 times 64. So, oh look, I'm seeing some pattern with 8, so I may not even have to take it that far, because this is 8 here, and this is 8 times 8. So I have 1, 2, 3, 4. So this would be the 4th root of 8 to the 4th, which would give me 8. So if that didn't make sense to you, if we want to talk about that more, about factor trees or what to look for, the more you do, we can sit down and talk. You can come to office hours. That's the time I set aside to speak with my students. I'm there in the Teams link, or we can make an appointment, talk about it more. Believe me, the more of these that you do, the more you're going to look for patterns, because your brain isn't going to want to work that hard. I promise. All right, so let's look at this. So it's so this is like a -1 times all this mess. So this is the cubed root of 8x to the 6th over the cubed root of 125. And so we talked about before that the cubed root of 8 is 2. And this will give me x squared. And then let's look at 125. It is, let's divide it by 5. So 125 divided by 5 gives me 25. And that's 5 times 5. So I have 1, 2, 3 5s. So that gives me 5 here. And that becomes negative 2x squared over 5. All right, one more. Big sigh. Okay, so this needs to be probably some sort of third. So I'm going to take 48 and divide it by 3. Why is it? Because I know that there's a radical 3 here. And so, let's see, 48 divided by 3 gives me 16. So let's look at 48. 3 times 16, and that's 4 times 4, or 2 times 2, 2 times 2. So there's 1, 2, 3, 4. So 16 equals 2 to the 4th. So this would become 8 4th roots of 3 minus the 4th root of 16 times 3, which would be 8 4 roots of 3. So this, because 2 to the 4th equals 16, that would be 2 4th roots of 3, and that gives me 6 4th roots of 3. Alright, so we can also write these without a radical symbol, and honestly that's a lot of times how I do them in my calculator. So a to the 1 over nth power is the same as the nth root of a. And we have rational exponents with numerators that are other than 1. So let's move down to the rule here. A to the m to the nth power is equal to the nth root of a to the nth power, or you can write it as the nth power of a to the m. And you'll see as we work these that one form will be easier than the other as we're simplifying. Alright, so we have an expression with a rational exponent, and we're going to write the expression as a radical. So you're going to determine the power by looking at the numerator of the exponent. You're going to determine the root by looking at the denominator of the exponent, and then use the base as the radicand, raise the radicand to the power, and use the root as the index. So I have 343 to the 2/3 power. So that would be, that's the radical, or the radicand. That's the third root of 343 squared, or you can write it as the third root of 343 quantity squared. And I think I like this one. No, I don't like that one better. I like this one better because I think it might be easier to simplify it and then square it. So let's look at 343. And I'm going to divide by 7. Let's see if what happens. 343 divided by 7. That's 49. So 7 times 49. That's 7 times 7. So that gives me 343 is 7 cubed. So that becomes 7 squared, or 49 is my answer. Alright, let's do 9 to the 5 halves. So I'm going to, this will be my radicand. So I have this, but we don't use the 2 typically. So it's just really the square root of 9 to the 5th. Or we can write it as the square root of 9 to the 5th. And that looks nicer to me because I already know that the square root of 9 is 3. And then 3 to the 5th, if you put that in your calculator, it would be 3 caret 5, and that gives me 243. Okay, last one, and then we're done with this section. Let's write this guy using a rational exponent. So, so the x is times all this mess, so it's x times, and then that would be 5y to the 9th divided by 2, because remember the square root is really a 2. Alright, you survived another section. Congratulations.